Okay, so the plan for today is to finish 1.4 multiplying whole numbers, start and hopefully finish 1.5 dividing whole numbers, and plan to start the next chapter, chapter 2, the language of algebra. So 2.1 just introduces some of the concepts of algebra, and then going throughout chapter 2, we introduce some more of the tools and techniques that we'll use throughout the course related to algebra. The quote of the day today is it's a paraphrase of a quote by Ralph Waldo Emerson. And this kind of sometimes happens that somebody makes a quote and it's, you know, not the catchiest way to say it or something. And over the years, people come up with kind of riffs off of that. So this is the version that I kind of like the most. What you do speaks so loudly that I cannot hear what you say. And it's a little bit like actions speak louder than words, but I think it really pushes that a lot further that actions speak so much louder than words that if there's discordance between them, the words don't even come through. And you can look at this from like the standpoint of if somebody else is looking at my life, are my actions in line with my words? Are they going to listen to what I'm saying? But I think an even better way to look at this is internally. So if, maybe if you were in an English class or something and they said, write a paragraph about the things that you value most in life, the things that are most important to you. A lot of people would write things having to do with family or friends or health or, lots of different things that people might value very highly. And then I think a good exercise is to think through that. What are my priorities in life ideally? And then to take a step back and maybe look at how you spend your resources. How do you spend your time, your energy, your talent, your cognition, your money? And what's the relationship between those two? Is there a concordance? Do they tend to kind of look roughly the same, what I value most and what I spend most of my, say, time on? Or is there discordance between the two? Is there a disagreement there? Um, I think especially these days, at least it seems this way to me, that it seems like we're being pulled in 20 different ways all of the time, and that this is, happening more today than it seems like it ever has before. I don't, I've didn't live 100 years ago, so who knows? Maybe it's just my bias of living in this time, um, but it's just so easy to say, okay, I want to do this, I want to go to the gym and work out, do something good for my health today, and then I get caught up watching TikTok videos and run out of time for that. Or, I want to make sure that I call my mom today, but I get caught up with arguing with people on Facebook or something and lose time there. So, um, I think it's good to check in with this every once in a while. So that's the quote of the day and a couple related thoughts for today. All right, so moving into multiplying whole numbers. We talked quite a bit about this last time, multiplying whole numbers, but we're going to continue on with multiplying without the block model. So we talked about the block model, what multiplication looks like. And let's take a look at approaching multiplication in a more what we might call something like algorithmic or kind of systematic way, in a way that we can apply to kind of problems of arbitrary size. So if we get numbers that are bigger, we can still handle that. So let's start with the idea of multiplying 14 times 3 with and without the block model. So if I thought of 14 times 3, I could think of that as being like 14, one rod, and 4 blocks. So this is 14. And I have it 3 times. It's 14 plus 14 plus 14. So here's another 14 and another 14. And I would like to add these together. So there are some then, if I take all of the blocks and put them together, I see that use a different color here. I see that these four plus these four makes 8, plus 2 more makes 10. That makes 1 rod. Left with 2 blocks left over that can't be put with anything else to form a rod. And then I have my 3 original rods. So I have 4 rods, 2 blocks. 14 times 3 is 42. Now I can approach this in a way that doesn't require me writing out rods and blocks and so on. How can I do this? So similar to like addition and subtraction, I'm going to write the two numbers 14 and 3, one above the other. I'm going to line up the place value. So the ones place of 14 lines up above the ones place of the 3. And then I'm going to indicate the operation that I'm doing just by putting it on the kind of bottom left here. Then I'll put a horizontal line to separate my factors, the things I'm multiplying together, from the product, from the result of the multiplication. Okay, so that was step 1. So I got everything kind of set up at this point. Now I multiply the digits in each place value. So I'm going to start with the ones place from the bottom number. In this case, my bottom number only has a ones place. Let me get rid of this little dot here. My bottom number 3 only has a ones place, so I'm going to start with that. I'm going to multiply by the ones digit in the top number, then by the tens digit in the top number, and so on. So what am I going to do? I'm going to take this 3 and multiply it by 4. After that, I'm going to take the 3 and multiply it by the 1, the tens digit. If I had a hundreds digit, I would continue on in this manner. Now I right away run into a problem because 3 times 4 is 12. That's a bigger, that's more than 1 digit, right? That's a bigger number than 9. What do I do with that? Oh, sorry. I just saw it pop up in the chat. Somebody said they can't hear me. Is there anybody else who can somebody post in chat if you are able to hear me, or
I can hear you just fine.
I heard somebody say something. Okay, it's all right. It seems like it's working now. All right, thank you. Yeah, I know occasionally I will turn off I'll like mute my volume. I've done this a couple of times before in Zoom meetings. I'll like have my volume muted for another reason. Like, I don't know if I had a tab in the background it started making noise and I muted it until I could find the tab and then I forgot to unmute it. Sometimes that happens to me. But all right, seems like it's working now. So, all right, thank you, everybody. Okay, so we ended up with 3 times 4, which is 12, is more than 9. So what do I do here? I do a similar thing to my addition. I carry. So in other words, I do 4, or well, let's say it this way. 3 times 4 equals 12. I have a 2 that comes down in the ones place. And then,
Sorry, I'm late. My other class ran over.
okay, you don't have to announce if you're late. That's fine. Yeah, if you come in late, just pop in. That's fine. 3 times 4 is 12. So the 2 comes down to the ones place. And this is related to
I
this.
can't hear.
All right. There we go. This 4 times 3 is 12 is related to these 3 groups of 4 that combine together to make 1 rod and 2 blocks. So we have the kind of 2 blocks here, and then we have this 1 rod, this one thing that looks more like the tens place. So that's going to carry over and look more like the tens place. Now here it gets, we have to be a little bit careful with things because I have this one up here in the tens place that was the carry. That was this one. But then I also have some things that represent the tens place, these original rods, these 3 rods. So when I do my next step, my next multiplication over, I'm going to do 3 times 1. So this is multiplied. And then I'm going to add the one that came over from the carry, plus 1. So I'm going to do 3 times 1. That's going to give me a 3. And then I'm going to add 1. That's going to give me a 4. So this is going to be 4 in the tens place. We start with our ones place, do 3 times 4. That gives us 12. Again, that was a number that doesn't have just one digit. So we need to know what to do with this extra digit 1 here. So we write down the 2. That represents kind of these 2 extra blocks. And we have the carry of the 1. Let me erase that and redraw it because it's getting a little messy. So then we carried the 1. That represented this 1 extra rod that 10 of those blocks came together and made 1 rod. Then we move to the next place over in the upper number. So we're multiplying the 3 times 1. 3 times 1 is 3. And then we add the 1 that was carried over. So 3 plus 1 is 4. That represents our 3 rods. That was the 3 times 1, or the 3 rods, plus the 1 additional rod that we got from that carry. So that's 4 rods, 4 in the tens place. So that's 42. Now, we want to really lean on doing this without the block model, because you can imagine for something like 14 times 3, it wasn't too bad to write out the rods and blocks. But if we had, 147 times 31, we definitely don't want to write that out. But we now have a procedure that we can go through, and we can carry out this procedure and just do a lot of small multiplications and a lot of small additions, multiplications like 4 times 3 or 3 times 1. And through doing a whole bunch of small multiplications and additions, and maybe combining those results, carefully, we can get the final answer. So that's really the goal of this process here. Okay, so let's look at another example like 17 times 4. So here we have 17 times 4. We're not going to use the block model now. We're just going to lean on the same method that we did up here. So the first thing we do is, again, we write out the numbers one above the other, line up the place values. We indicate that we're multiplying. We separate our answer with a horizontal line. Then what do we do next? So next we start working from right to left. We multiply the ones places together, then the ones place of the bottom number with the tens place of the top number, the hundreds place, if that applies, of the top number, and so on, making sure to carry when needed. So if I multiply my ones places together, I get 4 times 7. And remember that discussion of the times tables from last time. This is where knowing those times tables is so important. So being able to know right away that, okay, 4 times 7 is 28. If you haven't practiced the times tables, again, go through, a couple times a day, just write out the whole thing. You can make flashcards, you can do like Duolingo math, you can find lots of ways to just practice those over and over. If you spend 5 minutes a day, twice a day for a couple weeks, you'll get, very used to what all of these different small products are, the products of a single digit number with another single digit number. But here we have 4 times 7 is 28. this is 8 blocks and 2 rods. Or in other words, it's 8 in the ones place, and then we carry a 2. So we're done with the ones place on the top. Now we move over to the tens place. So for the tens place, I do a similar thing. I multiply 4 times 1. Now 4 times 1 is kind of the number of rods that I started with, so to speak. But I also had some extra rods that got made from combining together all of the different blocks that I had a couple of groups of those that I could combine together to make additional rods that made 2 additional rods, so plus 2. So 4 times 1 here, 4 times 1 is 4, and then plus 2 is 8. Okay, so we had 4 times 7 is 28. Write the 8, carry the 2. 4 times 1 is 4. Plus, oh, silly mistake. There's a lot going on in chat. If we can kind of, it's very distracting. If we can keep, people are sending me direct messages, and if we can keep chat to questions about the class, that would really be appreciated. So chat should really be questions about the class. If you want to ask me anything like about your grade or homework or anything, you can either pop into office hours, which are right after class, or you can send me an email about that. So yeah, if we can reserve the chat and the discussion in class for the class material, that way we can kind of stay on track, and then office hours and email and so on are better places for any individual questions. Okay, so let me fix this. 4 times 7 is 28, so we write the 8, carry the 2, and then 4 times 1 is 4, plus 2 is 6. I think sometimes when I'm saying one thing and writing another thing, I tend to write the wrong thing. So 4 plus 2 is 6. We now have 6 blocks that are 6 rods that come from the original 4 lots of 1 rod, plus the 2 additional rods that we were able to group together from all of the assorted blocks. So making a total of 6 rods. So 17 times 4 is 68. Now remember, we had some different ways of representing multiplication. One of them is with this kind of cross, this times sign. But we could also just write one number next to another number with parentheses. We can't write like 10 times 3 is like, we can't write it like this because that looks like 103. But if we just put parentheses around the 3, that makes it clear these are 2 different numbers, 10 and 3. And if we don't explicitly say what operation we're doing, that almost always means multiply. So in this case, we would do 10 times 3. Okay, so I want to do 10 times 3. So again, I write my 2 numbers one above the other. I typically write the number with more digits on top. It just tends to work out a little better that way. It's a little easier to do. I write my ones digit above the ones digit and so on. I indicate multiplication and separate the result from the factors. And I start with my ones place. 3 times 0, well, anything times 0 is 0. And then I go to my tens place. 3 times 1, well, anything times 1 is just itself. And there we go. This was an easier one. Our answer is just 30. When we're multiplying by 10, the result is actually pretty easy. If I did say 10 times 5. 5 times 0 is 0. 5 times 1 is 5. Right? All that I ended up doing was when multiplying by 10, I have my place values of ones, tens, hundreds, and so on. When I multiply by 10, I just move over to the next place value. So my 5, when I multiply by 10, just moves over one to the left and makes a 5 in the tens place. And then we have 0 ones. Or another way to look at it is if I started out with 5 blocks and I multiply this by 10, well, then I just have 9 more copies of 5 blocks, but each of those just makes one rod. So now instead of 5 blocks, when I multiply by 10, I have 5 rods, indicating 50. Or if I started out with, say, 50 and multiplied by 10, I would get 500. If I started out with 5 rods and multiplied by 10, each one of those rods would turn into 10 rods that would make one square, and I would end up with 5 squares. So when I multiply by 10, I basically just add a 0 to the end of my number. By add, I mean insert. So I kind of stick a 0 at the end of the number. 3 turns into 30, 5 turns into 50, 10 times 7 would be 70, 10 times 1 would be 10, and so on. Okay, what about 32 times 5? Remember, this was another possible way to write multiplication, just with kind of a dot between the two numbers. Note the difference between something like 32.5. We haven't talked about decimals yet, but I'm sure have seen decimals, before in math and in a lot of other applications. This is different than 32 times 5. So if the decimal is kind of in the middle, height-wise of the line, it's a multiplication. If it's at the bottom, it's a decimal point. Okay, but let's do 32 times 5. So again, we get everything set up. Ones place over the ones place. And then we start by multiplying our ones places. 5 times 2, well, that's 10. Again, if these products of single digit numbers aren't super easy for you, that's fine. We're working our way up to that with the times table. So probably the smaller ones are pretty easy, 3 times 3 or 2 times 4. But bigger ones like 5 times 7 or 9 times 8 might be more challenging. So just drill that times table over and over the span of a couple weeks, hit it a couple, like 2 to 3 times a day, and you'll get better and better at this. So 5 times 2, that makes 10. We write the 0 and we carry the 1. Then we have 5 times 3 is 15, but then we had to carry the 1, so plus 1 is 16. So here I end up with 16. And I mean, I suppose I could do like, right, a 6 carry a 1. But since I got all the way to the left and I don't have any more digits out here that I need to multiply by, it's actually not bad to just write 16 here, right? This 16 represents, because it starts in the tens place, it represents 6 rods and 1 square. And I don't have any other squares to combine it with because I've already done the 5 times 3 and there's nothing else out in front here I don't need to keep going with my multiplication problem. So I can just write down that, okay, I made one square. There's no other potential squares for that to have to combine with. The reason I couldn't do that for the 5 times 2 equals 10, I couldn't just write down 10, is because I had other rods from when I continue on with the multiplication that need to combine with that one rod. I had 15 from the multiplication, and then that one that carried, I need to combine those to make 16. So that's really the only reason that that I need to do this carry operation. If we wanted to really force the issue, you know, we could say, and keep rewinding until I get rid of that one. We could say, carry the one. And I could think of the number 32, 3 rods and 2 blocks, as being like 032, right? I could explicitly say 0 squares, 3 rods and 2 blocks. I could do the same operation that I did before. That wouldn't break things. It's just a little bit inefficient. I could say 5 times 0 plus the carry of 1, but 5 times 0 is just 0. So 0 plus 1 is 1. I get the same answer. So I could kind of force the issue and keep going with this process. Or I could just say, okay, I've kind of run out of stuff to multiply by. I'll just write the 16 as a 16. Whichever way you prefer to think about it, I think is fine. Right, let's look at a slightly bigger problem. We have a 3-digit number now multiplied by a single-digit number, 263 times 7. So again, we'll start with 263 times 7. And again, we'll be careful to kind of line up our ones above one another. We start on the right side, we do 7 times 3. And 7 times 3 is 21. So I write a 1 and I carry a 2. Right? This 7 groups of 3 blocks was able to be combined and make 2 rods, and then 1 block left over. I move over and I multiply my 7 ones by the 6 that's in the tens place. Well, 7 times 6 is 42. But then remember, I had those, so I have 42 rods from 7 groups of 6 rods. But I also had those 2 extra rods that came from combining together a whole bunch of blocks. So I have to add 2 to that. Giving me 44. So I write the 4, and then I carry the other 4. And then I go one step further. I now multiply my 7 against the hundreds place, against the 2. So I have 7 lots of 2 squares. But this 4 that I carried represents 4 more squares that came from combining together some of the rods. So plus 4. So 7 times 2, I have 7 groups of 2 squares from what I started with, but I was able to combine some rods together and make 4 more squares. 7 times 2 is 14, plus 4 is 18. Now I could write the 8, carry the 1, but I do notice that I don't have anything else remaining that I need to multiply by. There's not like a, 5 out here or something. I'm going to have to do another step. There's nothing else to multiply by. So I can really just write the full 18 on this line, representing 8 squares from the ones period, and then one kind of like super block, 1 block from the thousands period, 1 block from the next period up. Maybe I'll put a comma here to make it a little easier to read. And I have 1,841 as my answer. Okay, let's look at this problem, 37 times 54. We'll set it up the same way, right? 37 and 54 above one another. Do it so that the ones place is above the ones place, the tens above the tens, and so on. I have to be a little careful here how I approach this, though. I certainly don't want to take 54 times 7. I mean, I suppose I maybe could do that and go off to the side and figure out what that was, but that seems like a lot of, working a little bit here, working a little bit over there. That's going to get very complicated very quickly. I'd like to do everything kind of within this structure. So I'd like to do something like multiply 4 by 7 or multiply 5 times 7. But I have to have a way to do this systematically and to kind of combine those different results in a meaningful way. So the big difference now is up above, in all of the problems I looked at so far, one of my numbers was a single digit number. I had 14 times 3, a single digit number. 17 times 4, a single digit number. 10 times 3, 32 times 5, 263 times 7, single digit number. So even if one of my numbers has several digits to it, if the other one is a single digit number, I can use this kind of more, maybe easier strategy. If both of my numbers that I'm multiplying have more than one digit, have two or more digits, I have to be a little more careful. So let's go back up to let's go back up here and see what it says. Okay, working from right to left, start with the ones place in the bottom number, multiply the ones digit of the bottom number by the ones in the top, then by the tens and so on. We did the carry, we know how to do that. We write out these partial products. So when I have more than one digit in the bottom number, the result that I get, if I say just isolate the 4 for the time being, and just kind of pretend this was 37 times 4, I would get an answer here, but it wouldn't be the final answer. It would be a partial product. It would be only looking at the 4 by itself. And then I would have to do what? Well, I'd have to repeat for the tens place in the bottom number. So then I would look at the 5 separately. That would give me another partial product. That would give me kind of an answer that's related to the 5. If I had more places in my bottom number, a hundreds place, a thousands place, I would just keep doing that. I would get as many partial products as I need, looking at the ones place in the bottom number first, and then the tens place in the bottom number, and then the hundreds place in the bottom number. With each partial product, I insert a 0. We'll look at what that entails. And then the last step is we add the partial products to get the final product. So the last step is I have several different numbers here. What do I do to them? I add them. That's going to give me a number that is the final answer. So we can see if we're multiplying a number, even if it's a big number, by a single digit number, it's pretty straightforward. We basically just do our process and we get the answer straight away. But if we're multiplying two numbers, both of which have more than one digit, we have to do this whole partial products thing, get kind of, a part of the answer here, a part of the answer there, a part of the answer there, and then add them together to get the full answer. Okay, so let's look at how these partial products work, how the inserting the zeros and so on works. Let's go through this problem. So I have 37 times 54. The first thing I want to do is look at the 4 in isolation, the ones place of the bottom number. And basically what I do is I just kind of pretend that the 5 from the 54 isn't there. I just look at that 4. I treat it as if I was doing like 37 times 4 or 32 times 5. I just treat it like 37 times 4. What would I do here? 4 times 7 is 28. So I have an 8 in the ones place and I carry a 1. 4 times 3, that's this product. And then plus 1 plus the carry. Or that is 12 plus 1 or 13. I don't have anything else in front of the 37 that I'm multiplying by, at least as when the 4 where the 4 is concerned, right? From the perspective of the 4, my multiplication problem is done at this point. I'll just write this 13. Again, I'm being careful that the 8 up here represented ones. It's staying under the ones column. The 7 from 37 represents the ones place, the 4 from the 54, the ones place, and the 8 represents the ones place. The 3, the tens place, staying under the other 3 and 5 that represent tens. The 1, the hundreds place, is one more space over to the left. This gives me a partial product, the partial product having to do with the 4 from the 54. We have another component, though, to my second number. And that's the 5 that's in the tens place, or you can think of it as the 50. Now remember, when I multiply by, did I make a mistake? Oh yeah, I did. Yeah, thank you. 4 times 7 is 28. My carry is 2. 12 plus 2 is 14. Just being sloppy with my carrying there. So that should have been a carry of 2 up above. 4 times 3 is 12 plus 2 is 14. So 148. How did I switch those? There we go. Okay, so now looking at my 5 from the 54 in the tens place. When I do this multiplication, like 5 times 7, I really kind of realize that this is really kind of like 50 times 7. So really what I want my result to be, it's like 5 rods times 7. 7 lots of 5 rods. My answer should kind of start in terms of rods. So when it up here, when it says insert a 0 as a placeholder, to make sure that I don't mistakenly start by counting blocks when I'm really counting like 5 rods and then 7 groups of 5 rods. So I'm really should be counting rods. To make sure that I don't put that in the blocks column by accident, I'll insert a 0 here. So that way, when I do 5 times 7 is 35, and I write down my quote ones place from this answer, really I recognize that that's representing 5 rods, and then 30 rods will combine together to make 3 squares. So I write a 5 there. It's 5 times 7 is 35, and I carry a 3. And now I do my 5 times 3. This is like 5 rods times 30. I only write it as 5 times 3, but it is kind of like 30 groups of 5 rods, and then plus 3. 5 times 3 is 15, plus 3 is 18. Now, if I had more digits over here, I would write an 8, carry a 1. But since I've gotten to the end, I'll just write that 18. So this is my second partial product, and it's related to the 5 from the 54. So really what I'm saying here is in the green, I have 8 blocks, 4 rods, 1 square. In the red, I have 0 blocks, 5 rods, 8 squares, and one kind of super block, 1 block from the thousands period. And I want to combine those together. I want to add those. So now I just have 2 numbers that I'm adding together. So I'm kind of tacking on a second math problem at the end of this first math problem. So this 148 and this 1850 gives me kind of 2 pieces of the answer, and I add those together to get the complete answer. 8 plus 0 is 8, 4 plus 5 is 9, 8 plus 1 is 9, and 1 plus 0 is 1, or just bring down the 1. So my final answer is 1,998. That's 37 times 54. Now, there's a lot of steps to this, but 2 things to realize. One is we're kind of doing the same thing a few times. So we do something with the 4, we multiply it by the 7, then by the 3, but we do the same thing with the 5. We multiply it by the 7, then the 3. We have to remember to insert this 0 here, but it's kind of like, several runs of the same program. So once we're used to doing the problems that are like 37 times 4, once we kind of master that ability, we can just repeat that a few times to get our partial products. And then once we get all of our partial products written out, especially if we were careful to write all of the place values directly above one another, the addition should be pretty straightforward. We should be good at addition by now. We can just do this addition and get our final answer. So it's a lot of operations. It's a lot of individual multiplications or additions. But I think each operation is fairly straightforward. It's really the kind of strategy, what do I do first? What do I do next? That really is the challenge here. But after you go through it, 3 or 5 times, the strategy is a lot more clear. It's a little bit like, driving somewhere new. The first time you go there, it's really confusing and you're not exactly sure where to turn, or you don't recognize anything. But by the 3rd or 5th or 10th time you've driven there, it's the directions are a lot more clear. Okay, let's look at the product of 13 and 100, 13 times 100. Now, I do have a question, should I set it up as 13 on top and 100 on the bottom, or 100 on the top and 13 on the bottom? We remember that multiplication is commutative. So if I switch 13 times 100 to 100 times 13, I get the same number. Or if I change my setup to where the 100's on the top, 13 on the bottom, or the 13 on the top, 100 on the bottom, and I follow the same set of steps, I should get the same answer. However, if I choose a different one for top or bottom, that might make my my process of getting the answer a little easier or a little more challenging. I'll get the same answer in the end, but I might have to do more steps, or it might be more challenging to do. So I'm going to set it up this way, and then maybe as an exercise. And you can apply this exercise to the previous things as well. You could do 54 times 37, work through it and see if you get the same answer. As an exercise, what if you did 13 times 100? What if you did it this way? And there is a little shortcut that we can apply here. So look for a shortcut. see if you kind of notice something about how maybe the first partial product works, and see if you can come up with a shortcut, kind of a special case. But we're going to work through it this way. So I'm going to just kind of by default, I tend to put the smaller number on the bottom. So that way I have fewer partial products to work with and fewer things to add together at the end. 3 times 0 is 0, 3 times 0 is 0, 3 times 1 is 3. Then I move over to the one that's in the tens place in the 13. Again, I don't want to make the mistake of doing like 1 times 0 or 1 times whatever and putting that here for that first multiplication. So I insert a 0 to bump everything over one place to recognize that now I'm looking at counting numbers of rods. I'm counting numbers of rods, so my kind of first result should be in the rods category. Again, I do 1 times 0 is 0, 1 times 0 is 0, 1 times 1 is 1. And now I add, I get 0, 0, 3, 1. I kind of recognize that 13 times 100, multiplying by that 100, all that does is moves me 2 place values to the left. It turns blocks to rods and then rods to squares. Or you can think of it as turning blocks directly to squares. But I get 1,300 as the result. So we can see why multiplying by, say, like 10 or 100 is a very easy process if we recognize that special case. We can see it in the blocks, rods, and squares model, or we could see it in this more abstract way of doing things. If we look at what happens over here and we kind of look for a shortcut, we might recognize why this is happening. Okay, and then let's work on this problem. So this is going to be a more challenging problem, 327 times 418. So I have two 3-digit numbers multiplied together. But again, the process is just the same. Just because they're bigger numbers, the process doesn't change. I start with my ones digit in the bottom number. I multiply 8 times 7. That's 56. So I write a 6, carry the 5. I do 8 times 2 plus the 5 from the carry, 16 plus 5. That makes 21. So that gives me a 1 and a carry of 2. And then 8 times 3 plus my carry of 2. Well, 8 times 3 is 24. Plus 2, 24 plus 2 is 26. So I could write down a 6 and carry a 2, but I see that I've reached the end of this number. So I can just write down the full 26, no problem there. Okay, let me erase some of this scratch work in here. And now we'll move over to the tens place in the bottom number. And we'll essentially repeat the same thing. Now, again, because I'm looking at the tens place in the bottom number, I'm kind of thinking of starting off counting rods instead of starting off counting blocks. So I want to first insert a 0. That kind of pushes everything over to start in the rods column. And then I do 1 times 7. Well, that's just 7. So I just get a 7 here. I do 1 times 2. That's just 2. Note that kind of the 7 is in the ones place up here, but it gets kind of pushed over again, because now we're kind of counting rods instead of counting blocks to start with. So my partial products down here don't line up as nicely in the second or third partial product as they did originally. 1 times 2 is 2, no carry. 1 times 3 is 3. And we're done with the tens unit in the bottom number. We're done with multiplying by that 1. We have our second product, the second partial product, written down here. And now I'll look at the 4 in the hundreds place in the bottom number. Again, I'm kind of thinking of 4 hundreds or 4 blocks. I'm starting counting off, or sorry, 4 squares. I'm starting counting off squares instead of rods or blocks. So now, because I have moved over 1, that first arrow didn't line up right. Because I'm moved over 1 2 places, I insert 2 zeros to start with, to indicate that I'm now starting off by counting squares. I'm starting off by counting hundreds. So I start off with like 7 groups of 400. So that's naturally going into the hundreds place. Let me erase those little arrows because I want to draw different arrows. And now I do my multiplications just like before. I multiply 4 times 7 is 28. So I write an 8 and I carry a 2. I do 4 times 2 plus the 2 from the carry. 4 times 2 is 8 plus 2 is 10. I write a 0. I carry a 1. And then lastly, I do 4 times 3 plus the 1 from the carry is 12 plus 1 or 13. And I could, write a 3 carry a 1, but I see that, again, I have no more numbers up here to multiply by. So this partial product is done. I can just write 13. Note that I've been very careful this whole time to keep all of my place values appropriately lined up. If I get them all jumbled up, it's going to make it really hard to add later on and really error prone. My last step now is to add these 3 numbers together: 2,616, 3,270, and well, what is this number? This is 130,800. I have to add these 3 numbers all together. Let me clean up a couple of these arrows that I drew just so that they don't get in the way now that we're adding. And I, again, start at my rightmost place, my blocks, my ones digit. 6 plus 0 plus 0 is 6. My tens, 1 plus 7 plus 0 is 8. My hundreds are my squares. 8 plus 2 is 10, plus 6 is 16. So I write a 6, carry a 1. I gotta write that 1 a little bigger up here. In my thousands place, I have a 1 plus 2 plus 3 plus 0. That makes a 6. And then in my 10,000s or my 100,000s, I don't have any contribution other than the 3 and then the 1. So multiplying 327 by 418 gives me 136,686. Are there any questions on this? Okay, so let's look at a couple of application problems. I know a lot of times people don't like word problems, but one of the really nice things about word problems is it gives you some context, right? Like if I just look at these two numbers, I don't know whether this is a reasonable outcome or not. Maybe as I get more advanced, then I can, do things like rounding and I can say, okay, what do I think approximately is like, say, 300 times 400? Maybe I can do that more quickly and get a rough idea. But when I have context, that actually is helpful. So instead of looking at an application problem or a word problem and thinking, oh, these are more difficult, there are some benefits as well. I can make sure that, the units I end up with, if I'm supposed to end up with dollars, do I actually end up with dollars? Or if I'm supposed to end up with a speed, do I end up with like miles per hour? Do my units make sense? Or just does the number make sense in the context? Kanisha is making a quilt. She bought 6 cards of buttons and each card had 4 buttons on it. How many buttons did she buy? If you just imagine going to Joanne Fabrics or Michael's or whatever, and they have button cards on their display, and each one has 4 of them, and she picks up 6 of them. Did she buy 1,000 buttons? Well, no. Like that, it's pretty clear that she didn't buy an enormous number of buttons. She bought kind of a reasonable number of buttons. 6 cards with 4 buttons each. Like you could hold that in your hand pretty easily. She also didn't buy like, 2 buttons pretty clearly. So if I go through my multiplication and I get like, 1,800, something went wrong. Or if I go through my multiplication and I get like 3, well, I mean, she bought 6 cards of buttons and each one has 4 on it. Something went wrong there. So I actually have a really nice way to check the answer that I get after I go through, something like this, or I can check my answer for reasonability. Now, in this case, this is a pretty straightforward multiplication. She had 6 cards of buttons, and each one has 4 buttons. So she has like, one card with 1, 2, 3, 4 buttons, a second, and so on has 6 of these. So kind of what she has, she's bought 4 buttons plus 4 buttons plus 4 buttons 6 times, or she just has 6 times 4 buttons. Or 6 times 4 is 24 buttons. So this wasn't a super hard multiplication. It's not the kind of thing where we're going to make a huge error and end up with 1,000 or something like that. But the point is that we can say, okay, 24 buttons, that seems like a reasonable answer. All right, another example here. Javier owns 20 1-ounce gold coins and 55 1-ounce silver coins. Over the past year, the price of gold increased $571 per ounce, and the price of silver has increased $6 per ounce. How much money did Javier's bullion investment gain? So bullion meaning things like gold and silver, like precious metals. Right. So I mean, that's kind of in the financial news these days that gold and silver and some other precious metals, but mainly gold and silver, have really done well over the past couple of years. They've, really done better, probably better than the market, but certainly better than they historically have done. So if you own gold coins or silver coins, you're probably pretty happy right now. This also, might be a time to get out of the market. I'm not sure. Um, there's all kinds of debate about whether we've hit the top and are coming down or whether it's going to keep going up. Okay, so I want to know how much money the investment gained. And he has 20 coins, 20 gold coins. And each gold coin gained $571 in value. So from just gold, he gained $571 20 times, once each for each of the 20 coins. And then for silver, he has 55 of those coins, and each one of those gained $6 in value. Silver is worth a lot less than gold. Gold's worth like, it's usually nearly 100 times as expensive. And this is his gain from gold and his gain from silver, and I want to add those together. So this is what I want to do. I want to multiply 20 times 571. I want to multiply 55 times 6. That represents the gain from gold and the gain from silver, and then I add those two together to get his total gain on his investment. Okay, let's start with the answer for gold. 571 times 20. I do notice that my bottom number has more than one digit, so I'm going to have to be a little careful here. However, my ones digit is actually 0. This should give you a little bit of a hint for that exercise earlier. I notice if I multiply 0 times 1, I get 0. 0 times 7 is 0. 0 times 5 is 0. This entire first partial product is just 0. My next number is 2. I suppose I could write a 0 and then start writing the numbers here, but sometimes I can just actually take a shortcut. If this first partial product is 0, that kind of puts a 0 in the blocks place, so to speak, to start with. And then I can just do 2 times 1 is 2 and just write it kind of on the same line. 2 times 7 is 14. Write a 4, carry the 1. 2 times 5 is 10. Plus 1 is 11. So Javier gained $11,420 on just the gold side of the investment. What about the silver? We want to multiply 55 times 6. Here I have one number on the bottom, so I think this is going to be a more straightforward problem. 6 times 5 is 30, so I write a 0, carry the 3. 6 times 5 is 30 again, but now I have the 3 from the carry. So Javier gained $330 on the silver investment. Even though he has almost 3 times as many silver coins as gold coins, they're just not worth as much. So when they go up in value, they don't go up as much in value. Most of his investment gain is from the gold because he just has so much more money invested in gold. Then the last thing I want to do is add the two together. So I want to add 11,420 plus 330. And I start at my ones place. 0 plus 0 is 0. 3 plus 2 is 5. 4 plus 3 is 7. 1 plus 0, 1. 1 plus 0, 1. So Javier's total investment gain over this last year would be $11,750. Any questions so far? Okay, I think for time considerations, I'll leave this as an exercise. But we want to do 360 times 160 to get the area. This would be the area in square feet, and I'm going to cheat here. So I can give you the answer. 57,600 should be the answer that you get. So for this one, as an exercise, when you're going back through your notes, go through this one, work through it, make sure that you get this answer here, 57,600. And we're going to move on to dividing whole numbers. So we have about a half an hour left in class, so I want to make sure that we get at least a good start on this. Ideally, we'd get all the way through it, but with a half an hour, we might or might not. So what's the idea of dividing? Well, we have the arithmetic operation of division, like add, subtract, multiply, divide. But actually, the word divide kind of means something more generally, right? If I, if I make a cookie dough or whatever, I have a big lump of cookie dough and it says, divide it into 4 pieces and wrap them in plastic wrap and put them in the fridge. That means I like cut them into 4 pieces. So to divide means kind of to split up. So I could think of, for instance, taking these B's and splitting them into groups of 3. I could, maybe one way I could group them is like this. There's one group of 3. There's another group of 3. And there's a third group of 3. So I see I have 3 groups of 3 from these original 9 B's. Or I could think of it a slightly different way. I could say, maybe I have my frogs. I have 10 frogs here. I would like to split the frogs into 5 groups of equal sizes. So here I kind of told you what the size of each group of bees I want and asked how many groups I would have. I'd have 3 of those groups. Or I could say, how many groups do I want? And then I would report back to you what the size of each of those groups is. So if I, had 10 frogs and I had whatever, 5 friends that I wanted to gift frogs to for some reason, and I want to give them equal amounts, how many frogs do I give to each friend? I kind of see that I can split them up like this, right? Or another way that I could kind of think of this is I have like 5 empty bags. And I could start by putting like 1 frog in each bag. I have enough frogs that I could put 1 frog in each bag. Do I have any frogs left over? Sure, I still have the frogs from this line. Do I have enough frogs that I could put an additional frog into every bag? Yes, I do. So I could put a second frog into each bag. So each one is going to have 2 frogs. So I could do this kind of more visually, or I can do this more like trial and error. Do I have at least 5 frogs? Can I give at least 1 frog to every friend? Yes, I can. Okay, put 1 in each bag. And then like, forget about those ones. I have some left over. Can I give each friend another frog? Yes, I can. Put those ones in the bags, forget about them. Do I have any frogs left over to still give away? Nope, I've used all my frogs. So each group is of size 2. I can give each friend 2 frogs. So if I want to split 10 frogs, into 5 groups, then each group is of size 2. Kind of 2 different ways I can think about this problem. Okay, so we have some different words indicating division. So things like divided by, 10 divided by 5. The quotient of, we'll see in a minute what the word quotient means. Or even just the simple word over. So 10 over 5. A lot of times when we're verbalizing division, we say it that way. That's a little more informal maybe, but that's how we often say it. Some symbols indicating division. We have the thing here that's called the obolus. It looks like this. That's a symbol indicating division. I almost never use it because, for instance, 10, let's say 10 divided by 5 or 10 plus 5, these can look very similar, especially in the mathematical type setting. 10 plus 5 looks like this. 10 divided by 5 looks like that. If you see them right next to one another, it's easy to tell them apart. But if you're on a smaller screen, it's really hard if you're just seeing one of them to say like, wait, is that a divided by symbol or a plus? Right? Or if I write them carefully right next to one another, it's pretty easy to tell the difference. But if I'm just writing one or the other, it can sometimes be hard to tell. We can also write division as kind of a fraction like this, with a horizontal bar, a 10 on the top, a 5 on the bottom of the bar. And this is where that idea of like over comes from, like 10 over 5. So we want to take 10 frogs and divide them into, say, 5 equal sized groups. Sometimes we represent this instead of in this kind of more fancy notation, which sometimes doesn't typeset all that well. We represent it just as a slash. So this would be 10 divided by 5 equals 2. This one here. And then we have this symbol. It looks like this. There's not a good way to draw it so that it looks correct in Microsoft Word or in a lot of the different programs to type math. So kind of one way to draw it is to use a right parentheses and then make a number that has a bar over the top of it. So it's not great, but you can draw it by hand a lot easier than you can draw it in like the equation editor here. Or sometimes you'll see this symbol. So this symbol that just looks like this is representative of this idea. The thing coming before looks pretty much the same, but the thing coming after, might just not be under that that overline. Now be a little bit careful. These represent the same thing. So all 5 of these symbolic representations represent the same division problem. So in other words, this is 2 the same way that this is. The order of the number of frogs I have versus the number of bags that I'm putting them into kind of switches when we are in this notation. This is a notation. I actually don't think this thing has its own name. As far as I can tell, it's just called the long division symbol. It's a notation that we use when we're doing long division because we can kind of build the long division strategy right off of this symbol. It doesn't work as well to say, write the division problem like 10/5 equals 2 when I'm, say, doing long division, when I'm doing division by hand. But that's really the main use for this symbol here. And again, it's pretty hard to typeset. It's hard to like get computers to write it nicely. So most of the time that you see division written, most of the time it's in one of these 3 ways, and most of the time that I write it, it'll be in one of these 2. But for this section, I'll try to show lots of different ways of writing it. And then a little more about the word side of things. Not super, super important, but we have dividend over divisor equals quotient. So like the number of frogs would be the dividend, the thing that's going to be divided up. It's the thing that will be divided. The divisor is the thing doing the division in a sense. It's like the number of bags, it's the number of things that I'm dividing into. And then the quotient coming from kind of an ancient pre-Western language, this idea of quod is like how many, how much, something like that. So how many frogs go into each bag, that's the quotient too. So quite closely cognate with Latin. You can even see some elements of Greek in some of the less common dialects of ancient Greek. So this idea like quotient, that quote comes from or some relationship with our vocabulary to something like how many. So if I split 10 frogs into 5 bags, how many frogs go into each bag? What's the quotient? It's 2. I think the word quotient is used a lot more than dividend or divisor, but we're going to be using all of them. And again, note that in the long division way of writing things, the dividend goes under that little, that little kind of house kind of thing. And the divisor is what goes out in front. Whereas in, say, the slash notation, the dividend is out in front and the divisor is second. So just be a little bit careful with that. Okay, so let's look at modeling division. If we model 14 divided by 7, I'm just going to draw little circles. We'll call them counters. We're not going to use the rods and blocks and squares so much here because when we're splitting things apart all over the place, like I don't want to deal with having a whole bunch of rods and having to split them apart and all of that. Okay, so I put 14 circles here. Some of them are kind of running into one another. And I want to divide them in, I can either think into 7 groups or in groups of 7. So if I want to group together 7 of these, I can group together, say, these first 5 in that first line with 2 from the next line. That makes a first group of 7. And then I ask, okay, I have some that have not been grouped together yet. Do I have enough to make another grouping of 7? Yeah, I do. I actually have just enough to make a second grouping of 7. So I could split 14 into exactly 2 groups of 7. So 14 divided by 7 equals 2, because 14 can be split perfectly into 2 groups of 7. Now you can probably imagine that we could have a situation where we can't split evenly. We'll handle that later on in this section. So for right now, we're looking at examples that do split nicely. All right, if I look at modeling 28 over 2 or 28 divided by 2, so there are 28 little circles. How many groups of 2 can I make? I can make a bunch. So let me just start making groups of 2. There's 1, 2, 3, 4, and 5. Still a bunch left over. I can keep making groups of 2. 6, 7, 8, 9, 10. So I've made 10 groups of 2 so far. I still have at least 2 more, so I can make another group of 2. Have at least 2 more, I can make another group. And another. And then one last group. I see that 28 can be split into groups of 2, and I can make 14 such groups. So 28 over 2 equals 14. Okay, so the counter model, it's a little bit nice when we have smaller numbers. It's intuitive. can we work our way up to dividing numbers without using counters? Obviously, it's going to be cumbersome if we have 575 over 5 or something. I don't want to write that many counters. So what does 28 over 2 look like? Well, I draw, um, oops, I don't know why I have the same one written here twice. Okay. I draw my long division symbol. Now remember, the number of counters that I start with in the slash notation, that comes first, comes to the left, but in the long division notation, that goes under this little sign. It comes to the right. And the divisor, the size of the groups that I'm dividing into, comes after the slash, comes to the right of the slash, but comes before my long division notation. So that kind of switches sides. Really easy to make a mistake and get the wrong thing underneath the long division sign and the wrong thing out in front of it. What's my process here? Well, my process is I look at my divisor 2. I actually start at my leftmost side. So this is a bit different than we've seen before. We go left to right. And I ask, does the number 2 go into the number 2? Does 2 go into 2? Or in other words, is this number that's coming from the dividend, that's coming from the inside of the long division sign, is that number bigger than the divisor? Yes, it is. How many times can I put 2 into 2? Well, 2 goes into 2 once. Let me try to get rid of this arrow. So 2 goes into 2 one time. I multiply 1 times 2, giving me 2. Because it goes in exactly one time, I subtract off 2 minus 2 is 0. I bring down an 8 like this. We're going through this kind of quickly. We're going to take this and split it apart piece by piece, but I want to go through it once on kind of a simpler problem that we just did to show, to give kind of some idea of how maybe the two relate to one another. So I did this process. Does 2 go into 2? Yes, it does. How many times? Exactly one time in this case. 1 times 2 is 2. Like once I kind of account for the one time that the 2 goes into the 2, all of the tens places have been accounted for. They've been accounted for with this 1. I have no tens places left over, but I still do have some ones places. So I bring those down. I look at the ones places next, along with any tens that might still be left over, but I don't have any left over in this case. Does 2 go into 8? In other words, is 8 bigger than 2? Yes, it is. 2 times what number gives me 8? Well, I know that 2 times 4 gives me 8. Right? I can put 2 into 8 once, certainly. Twice, 2 times 2 is 4. That's still not more than 8. 3 times, 6. 2 times 3 is 6. That's still not more than 8. I can put it in 4 times. 2 times 4 is 8. That gets me right on that border. If I tried to put 2 into 8 5 times, 2 times 5 is 10. That's bigger than 8. I don't have enough to satisfy that. 2 goes into 8 4 times. 4 times 2 is 8. I subtract off this 4 is accounting for 8 in the ones place. 4 times 2. I have 2 lots of 4 from the ones place. So all of my ones have been accounted for. I have none left over. And there's my answer, 14. So I can say 28 divided by 2 equals 14. So here I'm looking, when I'm doing long division, I'm looking at a different perspective than when I'm doing dividing by counters like this. It's a little bit of a different perspective. One way I can do division is by continuing to subtract off units of the divisor, right? Basically what I did is I started with 28 counters. I subtracted off the divisor of 2 ones. I kind of grouped 2 of them together, set them off to the side, and said, can I continue grouping in groups of 2? Yeah, I have enough left that I can continue grouping. I'll group another 2. I'll subtract them off. I'll kind of group them together, set them off to the side. Do I have enough counters left over? I can keep going. And I just do that over and over. And when I get to, say, the 13th one, I have now grouped together in groups of 2 most of my counters. I still have 2 of them left over, and I can group those into one final group of 2 to make 14 total groups of 2. Right? So up here, I'm doing kind of like I start with 28, I subtract 2 to give me 26, and I increment my number of groups by 1. I subtract 2 again to give me 24 that are left over, and now I have 2 groups. So I have 2 groups of 2 plus 24 that are ungrouped. I subtract 2 again, I get 22 left over and 3 groups of 2. So that's kind of the approach that I'm taking up here if I was to write it more mathematically. This is pretty cumbersome though. So what am I kind of asking down here? I'm saying, well, 28 is kind of like having, well, it's not kind of like, it is like having 2 rods and 8 blocks. If I want to split these into groups of 2, if I have 2 bags down here, or sorry, if I want to split them into 2 groups, not groups of 2, if I want to split them into 2 groups, if I look at this a little bit differently, I can start with my rods since they're kind of the biggest unit that I have. I see that I do have 2 rods. Since I have 2 rods, I can just put one of them in each bag. That takes care of 20 of my counters right off the bat with one operation. That's much more efficient than doing 10 of these little subtractions of 2s, right? So I now have in each bag, I have 1 rod, and these ones are no longer sitting out here. They've been placed into bags. And then I have some blocks. Can I split these 8 blocks into 2 equal sized groups? Yeah, I can. I can take these 4 and then these 4, and that's 2 equal sized groups. I can dump these in here, dump these in this one. And my 8 blocks get split into 2 groups of 4 blocks. Each of my bags has 1 rod and 4 blocks, 14. So I'm just kind of switching maybe my perspective. Instead of saying group and groups of 2, I'm saying give me 2 equal sized groups. Put, as many rods as you can into those bags first. Now I got rid of the rods. I got rid of the biggest unit first. I was able to do in one operation what it took me 10 operations to do up here, right? To split up these 20 counters. That was a lot of circling and labeling and all of that. But I was able to do that in just one operation down here instead of whatever 10 operations up there. So it's more efficient to think of it this way, maybe when we're going through and doing a computation. And again, if you didn't follow all of the long division steps, that's okay. We're going to kind of work through long division carefully and go through a lot of examples, but I wanted to do these one right after the other, just to kind of show when we go through this process, when we're asking how many times does the divisor go into the biggest number, why are we looking at the biggest number first when all of our like multiplication, addition, subtraction started by looking at the smallest numbers first, the smallest place values? And this is why we're trying to kind of, make things very efficient. We're trying to divide, if I had squares, I'd want to start with the squares, putting them into bags. I wouldn't want to break the squares up into a bunch of tiny little blocks and then sit here and sort blocks all day long. Now, what if I have something like this, 29 divided by 29? Well, again, there's two ways I can think of this. If I have 29 individual things, so say 29 of these total, how many groups of 29 can I make out of that? Well, if I have 29 individual things, I can only make one group of size 29. Or another way to think about it, if I have 29 individual things and I have 29 friends that I want to give them to, and I want to give them an equal amount, how many can I give to each friend? Just one that I can give to each friend. So if I had 29 things and I wanted to split them into 29 bags, I would have to put just one in each bag. 29 divided by 29 is 1. And really, any number divided by itself, so long as that number is not 0, because I don't know what it means to have 0 things and try to put them in 0 bags. But any number divided by itself turns out to be 1. Okay, so I think the last thing we'll talk about today is some of these division properties. We have two division properties related to one, that multiplicative identity, the thing that if I multiply a number by it, I get the original number back. 5 times 1 is 5, A times 1 is A. So one of my division properties is that, for instance, 5 divided by 5 equals 1, or 3 divided by 3 equals 1, or A divided by A equals 1 if we wanted to use letters or variables. We're jumping ahead a little bit here, kind of teasing the next chapter. So long as A is not 0. We don't want to do 0 divided by 0. Because I don't really know what it means to have 0 things and try to put them in 0 bags. That seems like kind of a silly question to ask. So any number divided by itself, as long as it's not 0, gives the result 1. And similarly, any number divided by 1 gives the original number back. And maybe I'll say actually B divided by 1 equals B. And here B can be any number. B can be 0. 0 divided by 1 is 0. If I have 0 things they hand out and I want to give them to one friend, how many things can I give them? I don't have any things to give my one friend. I can't give them any things. So these are my two division properties. Any non-zero number divided by itself is 1. Any number divided by 1 is that number. We have two division properties of 0. For instance, like 0 over 5. If I have 5 friends and I want to give them some stuff, but I have 0 things to give them, how much can I give each friend? Well, 0. Or 0 over A equals 0, as long as A is not 0 itself. On the other hand, if I try to divide by 0, if I have one thing and I have no friends, how many friends can I give one thing to? Or how many things does each friend get if I have no? Well, this doesn't really make sense. So we say this is undefined. We don't want to divide by 0. I'm going to say B over 0 is undefined. So 0 over a number, like 0 over 3, that's fine. If I have 3 bags and I have 0 pieces of candy to allocate between the bags, I just put 0 candy in the bags. That's a sensible thing. But if I have like 1 piece of candy and no trick-or-treaters, how much candy can I give each trick-or-treater? Well, I don't have any trick-or-treaters. That's not really a sensible question to ask. And then maybe the last thing that we'll ask is, well, multiplication of this nice commutative property, I could switch the order, maybe in a way that's more convenient to me or whatever. And I got the same answer. Does that apply to division? In other words, is 10 divided by 2 equal to 2 divided by 10? And the answer is no, because here there's not really a symmetry between the dividend and the divisor. The dividend is the number of things I have, and the divisor is the number of ways I want to split it up. 10 over 2 is 5, because if I have like 10 pieces of candy and 2 bags to put them in for trick-or-treaters, I can put 5 in each bag. 2 over 10 clearly is not the same thing, because if I have 2 pieces of candy and 10 trick-or-treaters, I run out of candy before I even give each trick-or-treater 1. So these are not equal. The commutative property does not apply to division. We can't switch the order of division and end up with the same result. So similar to how like we had some nice properties for addition, but most of them didn't carry over so nicely to subtraction. We have some nice properties for multiplication, but they don't carry over so nicely to division. The commutative property doesn't carry over. We have potential issues when, say, dividing by 0, where when multiplying by 0 was super easy. We just get 0 as the result. So division is related to multiplication, but the properties don't all carry over. So we have to be careful with that. Okay, so when we come back, we will finish up this section on division. We'll finish up chapter 1, and then we'll start in chapter 2. We will be picking up the pace in chapter 2. We've been going somewhat slowly in chapter 1 just to kind of get our feet under us and get some momentum. In chapter 2, we'll start speeding up. So I do strongly recommend that you read ahead, that you work some problems in the book ahead of class, so that when you come into class, you're kind of prepared for what we're going to be covering. And then, shortly after class, within maybe that same day or the next day, work some problems on the homework to make sure that you understand what was covered in class, and then you can ask questions either the next class or office hours, and that you don't end up waiting till the last minute to do the homework. All right. So I will be in office hours. Give me about 5 or 10 minutes or so just to kind of get everything turned around on my end. But I'll be in office hours shortly. The Zoom link is on the Blackboard site if you want to join that. Otherwise, have a nice long weekend, and I will see you next week. Have a good one.
Thank you.